For PHYS206, we were seeing complex numbers and functions. We are now continuing to find roots now. Roots of complex numbers or equations. Okay, so the first example that I would like to solve is this. Find roots of 1 minus I to the power of 1/3. So, in other words, what z values make this 0? Okay? So, we would like to now find out, we have to write this as r times e to the I theta, or I some function here, right? So z is given like that, but for z is equal to 1 minus I, we see that x equals 1, but y equals minus 1. Because if z is given by x plus iy, okay, it is, we have this x and y values. In this case, r is the square root of squares of this x. 1 square plus minus 1 square gives you square root of 2. And the angle now should give you this. So if x equals 1, it is square root of 2 times cosine theta. And y equals minus 1, it's square root of 2 times sine theta. Okay, let me draw the complex plane again. So this is real z, which is x, and this is imaginary z, which is y. Okay, so now if you have number x equals 1, y equals minus 1 is right there. Okay, it's just 45 degrees here from here. Okay, so this is 1 minus I, right there. So we would like to now get these angles. So what kind of angle we have? Actually, it's the same angle as 45 degrees, but y value is negative, x value is positive. So for this one, remember that this x was r times, if this is r, which is the radius, cosine theta, and y was r sine theta, okay? In this case, we have now x and y values different, but this is not the angle, but the angle is this one, okay? Because r point is right there. 1 minus I is in the fourth quadrant. So this angle, as you see, is 180 degrees, okay, plus another 90 degrees, and then plus another 45 degrees. So it turns out it's 315 degrees, okay? So how can we write 315 degrees? It's 3 pi over 2 plus pi over 4. 3 pi over 2 is 270 degrees until here, and then we add one more pi over 4. It's just 7 pi over 4. So we found the angle. The angle is known, okay? The angle is known. So also from this, as you see, x over y, if you divide each side by side, okay, tangent theta will give you minus 1. So it means that if tangent theta is minus 1, it can only be in the fourth quadrant over there. Here, tangent theta is positive. Here, tangent theta is also negative, but we have to have now y value, which is negative, but x value, which is positive. So this is the only quadrant we have here. So this is the reason that we get this angle. So this is the angle that we obtain. Okay, in this case, 1 minus I can be written as 1 minus I only. See, I'm only writing 1 minus I. I haven't taken the cube root of it. Is given by square root of 2 times e to the I, 7 pi over 4 plus 2k pi. We always add this as the phase, because this phase will determine us the roots of this equation. Since this is the cube root, probably we will get 3 roots, okay? So k will go from 0 to 1 and 2. So we will change k like that. But we are not done yet, because it's just 1 minus I. We have to get the cube root of this side by side. So if we can get the cube root of this, and we have to get the cube root of everything on the right hand side. Okay. So now, so 1 minus I cube root will be equal to square root of 2 cube root times e to the I over 3. Taking the cube root of this exponential is just multiplying this coefficient by 1 over 3. So it's I over 3, then 7 pi over 4 plus 2k pi. Okay, so this is it. So we have done it. So this is how you can represent this thing. Instead of 1 minus I, we can write this as like that in polar form. Okay, so we know that e to the I theta is cosine theta plus I sine theta. Okay, so now we can write this in cosine and sine, so that this is now 2 to the 1/6. Okay, so 2 to the 1/6 times cosine of 7 pi plus 8k pi over 3, okay, plus I sine 7 pi plus 8k pi over 3. So what happened is that here we multiply the top and the bottom by 2, so this became 4 divided by 4, okay, so that so it was 2 there, multiplying by 4, it gave 8. So this, instead of 2, I've written 8 over 4, so that the denominators are the same. If 4 is multiplied by 3, okay, we can get 12. So this is 12 on the denominator here, 12. Okay, so this is the root. Okay, this is the root. So this, so if we say, that k equals 0, then one of the roots will be given as 2 to the 1/6 times cosine 7 pi over 12 plus I sine 7 pi over 12. So this is root number 1. Okay, everything should be multiplied by this 2 to the 16, and then z2 is when k equals 2 here. When k equals 2, it's just pi, you just add pi, so that 7 pi over 12 gives you, okay, 7 pi over 12. Let's add it here, 7 pi over 12 plus k equals 1. 8 over 12, okay? 7 pi plus 8 pi, which is 15 pi over 12. So 2 to the 16, 1 over 6 times cosine, okay, 15 pi over 12 plus I sine 15 pi over 12, okay? So this is the second root, the third root being the last one, okay? 2 to the 1/6 times cosine. Now k is 2. When k is 2, okay, when k is 2, then this is 16 plus 7 is 23 over 12. So 7, 15, 23. Pi over 12, okay, I plus I sine 23 pi over 12. So we get 3 roots. Okay, for those of you who can relate a little bit, we are trying to find the roots of this function, okay, this equation. So this is just a complex number. So if the complex number is written like that, okay, we can get r, which is the radius of this circle, which is the magnitude, and then the angle part is just obtained from here. As you see, y equals r sine theta, and x equals cosine theta. From this, you can get tangent theta as y over x. So if you know y and x values, you can easily get the angle theta. So for this one, since z x plus iy is given by 1 minus I, x equals 1 and y equals minus 1, as you see. In this case, we can get the magnitude by just taking the squares of each x and y, and then add them up, get the square root. It gives you square root of 2, so that now we can get, now our purpose is to get the angle, but the angle, if you get sine theta over cosine theta, you see that since x equals 1 and y equals minus 1, gives you tangent theta, which is minus 1. From this, we can find that this must be angle 315 degrees, okay, right there. So it's also this number that is put here. So its x value is 1 right there, and y value is minus 1. So this is the point on the complex plane. And as you see, the angle that this point makes with this complex plane is either minus 45 degrees, okay, minus 45 degrees, or plus 315 degrees, okay. So now we get 3 pi over 2 plus pi over 4 gives you 7 pi over 4. This is 315 degrees. So after having determined the angle, we can write now the complex number like that. 1 minus I is this, okay, square root of 2 times e to the 7 pi over 4 plus, the important point is that 2k pi, this is the phase that you have to add. This is very important. Otherwise, you cannot get 3 roots. Why do we need 3 roots? Because this is the third order equation. So third order equation gives you 3 roots. Okay, it's like cubic equation, but the inverse of it. Okay, so after writing 1 minus I like that, all you have to do is just take 1 over third power. In other words, cube root. So to get the cube root of right hand side, it's very simple. You have the cube root of each square root of 2 and this exponential term, and then it gives you square root of 2 to the power of 1/3 e to the I over 3 times whatever the phase is. Okay. Now, if 3 is multiplying this, you get 12 on the denominator, and this is what you have. So that now you have exactly 1 minus I 1 over 3. So this is equal to that. So when this is 0, this is only possible when for different k values. Okay. So this will become 0 at k equals 0, 1, and 2. So for k equals 0, k equals 1, and k equals 2, we can put the values there and then get 3 different roots, and this is it. As you see, the roots are also complex. So these are just numbers. Cosine 7 pi over 12 and sine, for instance, 23 pi over 12 is just a number, and 2 to the power of 1/6 is also some kind of number which is smaller than 1, and then you can just get you can just multiply these numbers to get individual complex roots. So when you put these complex roots into this 1 minus I to the cube root, it gives you exactly 0. So either you put this one or that one or this one, okay, you will get 0 for the root. So this is the first example to be solved. Any questions? Okay, so we continue now solving another example. Since this is being recorded, you can get also the video, so you can get the solution easily. Okay, so suppose that in the second example here, suppose that you have a z square plus bz plus c equals 0. As you see, this is second order equation, but in complex form. But the roots are still minus b plus and minus square root of b square minus 4ac divided by 2a. Okay, so the roots. So let's give an example. So suppose that you have two. In this case, a cannot be 0, by the way, because when a is 0, this denominator blows up. It doesn't work, because when a is equal to 0, the solution is just minus c over b, right? So anyway, so say that you're solving 2z squared plus 6z plus 1, let's say minus 1, okay, is equal to 0. Okay. Okay, let's get plus 1. So how can we get the roots of this? How can we get the roots of this? Let's change it a little bit here. Instead of this, let's say z plus 6, like that. Okay. So now b is 1, a is 2, and c is 6. In this case, the roots z1, 2 here, the roots are given as minus b, which is just minus 1, okay, plus and minus square root of b squared, which is just 1, minus 4ac. So the product of a and c is just 12 times 4 is, okay, 12 times 4 is 58, okay, 58 divided by 2a, which is just 4. 2 times 2 is 4, okay? Is this okay? Okay, 2 times 4 is 8, 48. This is 48, sorry, not 58. So basically this is just minus 47. So z12 is equal to minus 1 plus and minus square root of minus 47 here divided by 4. But minus 47 can be written as just I times square root of 7. Okay, minus 1 plus and minus I square root of 7. 47 divided by 4. So the roots are, one of them is minus 1 plus square root of 47i divided by 4, and the other root is minus 1 again, minus, in this case, square root of 47 times I, everything divided by 4. So these are the two roots of this second order equation. Good. So now, as you see, this is the same kind of analysis we have, but when we have minus 1 under the square root, it's written as square root of I squared, but I squared goes out as I. So wherever you see minus 1, you can, square root of minus 1, you can write it as I, okay? Minus 1 equals I, because if you take the squares of both sides, you see that the square of I gives you minus 1. So this is complex number. Okay, so we found the roots of this second order equation. Now I would like to solve another example. Okay, in this example now we have, okay, we have this equation. Z to the 4 equals minus 16. If z to the 4 was plus 16, it would have been easy. It would be just 2 and minus 2 or something. We could easily find, but now it's minus, so we have to be careful with this. So now, since z is written as x plus iy to the power of 4 is minus 16, so how can we write this in polar form? The first thing is to write this in polar form, okay? So if we choose x equals minus 16 and y equals 0, then cosine theta will be equal to y over x, which is just 0. Cosine theta is 0. So let's see, okay, this is it. Cosine, this, how did we come up with this number? Because the r, which is the r, remember that is the square root of squares of x squared and y squared. When you add them up, you should be able to get just 16 somehow. But it's only possible that you can get one of them negative. So 16 squared gives you 16. So this is 16. This is good, 16. But now we need minus 1. 16 times e to do something will give you minus. So how can we write this as minus 1? Okay, so this will go into minus 1. So in this case, we know that if from here, if tangent theta, okay, is equal to 0, sorry, this is not the cosine theta, but tangent theta. Tangent theta, which is y over x, should be 0. If tangent theta is 0, then theta should be equal to pi, okay, pi. As you see, here x is minus 16, but y is 0. On the complex plane, if this is real z and this is imaginary z, okay, it's just here. It's minus 16. So this is the point. And you see, this angle is just nothing but 180 degrees. So This is given by that. So basically, minus 16 is just nothing but 16 times like cosine pi, because cosine pi is also minus 1. It can be written like that. But instead of this, we write minus 16, which is equal to z to the 4, which is equal to 16 times, okay, 16 times e to the I pi. But now we have to add the phases, 2k pi. We always add 2k pi, okay? How many times are we adding here? Because this is fourth order, 4 times. So k will go from 0, 1, 2, and 3. So e to the I pi plus 2k pi, okay, will give you the phase of it. So this, as you see, each one of these exponential term where k is 0, 1, 2, 3 will give you minus 1 exactly, so that you will have minus 16. So basically, then the solution is that you have to get now the cube root, fourth root of this, okay, expression, so that z will be equal to 16 to the 1/4, okay. Now e to the I over 4 pi plus 2k pi. After this part, you have to get to solve this. Of course, the solution of this is very simple because it's just 1/4, right? You take 1/4 power of each side, and then the result is just given by that. So simply, this is what we have done. So this is z values, which make this is equal to 16, or just z to the 4 plus 16 is equal to 0. So these are the z values, okay, that satisfies this equation. So now we have to run k from 0 to 1, 2, 3, and then we will get the result. So for k equals 0, one of the root is just 16 to the power of 1/4, okay, 1/4. So what is it? Actually, 16 is just 2 to the 4, right? 2 to the 4 is 16. But if you take 1/4 power of this, it's just 2. So basically, the coefficient is not 16, but z2 here, 2 times. So this is 2 e to the, okay, I over 4. Now, the angle k is 0, just pi. So I pi over 2. So this is one of the root. So this is z1. Excuse me. Alo. Bir saniye, telefonu veriyorum. Şu telefona baksanıza. Canan. Telefona bak benim. Okay. Okay, so for k equals 1, we have to get this one here, so that pi plus 2 pi is 3 pi. So z2 is equal to 2 times e to the 3 pi over 4 I. Of course, there is I there. Okay, and then z3 is 2 e to the, now we add, this is for k equals, this is k equals 0, this is k equals 1, k equals 2, okay, k equals 2, so pi plus 4 pi, which is 5 pi over 4i, and then z4 is equal to 2 e to the 7 pi over 4i. So this is k equals 3. So these are the roots of this equation. Okay. So when we put here, we get exactly minus 16. Okay. Because if you take take this one for instance. Okay. So if you take the fourth power of this right hand side, it's just 2 to the 4 times e to the fourth power is just 7 pi I. But this is now 16, but this is cosine of 7 pi plus I sine 7 pi. Okay? So this is the odd product of pi. So sine will always give you 0, and cosine 7 pi, which is odd number, okay, gives you just -1, so it's equal to -16. So it checks. So if you put all these values into this equation, you get the solution. Okay. So the solution of this equation is just 4 of them, and it's for k equals 0, 1, 2, 3, and these are given by these values. Okay, so we obtain this solution. Okay, so this is the end of the examples. Now we again we do some kind of, we continue with some functions now. Okay, for the complex thing. So we have learned how to treat the complex numbers. Now we have now complex functions. How can we deal with complex functions? Since z was given by x plus or minus iy, the complex function will give you by omega, which is f of z, it is given by uxy plus I vxy. As you see, this part is the real part, but this part is the imaginary part, or complex part. Okay? So now we have z plane and omega plane. So what's happening is that suppose that we have some kind of function. Say omega equals z squared. This is the function of z, as you see, the square of the complex number z. So how can we represent this in z plane and b plane, w plane, when a 2, 1 and b 0, -1 points are chosen in z plane? So now in z plane we place this here. Okay, so this is real x and this is imaginary imaginary z, real z. Okay, the first one is 2, 1 is right there. This is 2 and then 1, right? This is the first point A, and the second point is just 0, -1. It's 0 here for -1 right there. This is B. Okay, so these 2 points in the complex plane, okay, is just these 2 points. So okay. So now, how can we find the correspondent points in W plane? So when you take z squared, which is the function, so this is uxy and this is vxy. So this is imaginary imaginary W or f, imaginary of f, and this is real of f, real of f. But f happens to be just square of z, okay? Square of z. Now, how can we do this? So let's get u and v points. Okay, so what we do is this, okay? Since we have now z squared, which is just a simple square of this function, so we just get z squared, which is equal to x plus iy squared, okay, iy squared, and then this, the square of this is just x squared plus 2ixy plus I squared y squared, but this I squared is -1, so that you can write this as real part separately and imaginary part separately. X squared minus y squared, and then there is an imaginary part which is this I times just 2xy, 2xy. As you see, after taking the square of this function z, we obtain this real and imaginary part. This is the real part. U is given by this, and then v is given by that. So we have u and v. Okay. Now let's write u and v separately. Okay. Let's do that here. Okay. Now u is equal to just x squared minus y squared, but v is equal to just 2xy. Okay. Now the first point, for point A, point A, remember that we had 2, 1 here, x equals 2, y equals 1, okay? When we insert these values here, u becomes 2 square minus 1 square, which is just 1, no, 3, okay, 3, but v becomes just 2 times 1, which is just 4, so 3, 4. So this corresponds to 3, 4, okay? So this point A, 2, 1, corresponds to A prime, what was it? 3, 3, 4, right? 3, 4, okay? 3 there and then 4 there. So this point A corresponds to 3, 4 in imaginary complex plane of function f. So 3 and 4. 1, 2, 3 and 4 right there. This is A prime. Okay. So this point corresponds to that one. And then let's find point B now. Point B. Now for point B, we have, remember that x equals 0 and y equals minus 1. X equals 0 and y equals minus 1. When we insert these values here, u becomes, okay, 0 square minus 1 square. And then v becomes 2 times 0 times minus 1. Okay, this gives you 0. V is 0, but this is just minus 1. Okay, because the square of minus 1 is just 1, and there is another minus sign. So we have now, for B, point B, which is 0 and minus 1, we have now B prime on complex plane. This point corresponds to just minus 1 and 0. Let's put that in here, minus 1 and 0 right there, B prime. So if you are going from A to B by this way in complex plane, it means that you are going to A prime to B prime in the complex function plane. Okay, so complex plane and W plane. So this is Z plane. This is W plane. Sometimes it's called F of Z plane. So two different planes. So now let's see how we can go, what kind of path we can follow. So in the first example, it is said that let's go from A to B, okay, in a straight line. Okay, if we go A to B in a straight line, let's draw it as a straight line like that. Okay, so how do we go from this point to that point in the complex function plane? How do we go? So this straight line corresponds to what kind of curve on this plane? Okay, it's not going to be straight line because it's squared. So now what happens? So if you look at here, we have now we can write some equation for this. As you see, for the equation, linear equation, y equals x minus 1. Why did we write this? Because as you see, at x equals minus 1, x equals 1, y is 0, but x equals 0, y is minus 1, and x equals 2, y is just 1. So we know that this is the equation for this one. So we found the function. Okay, now we can use this property, okay, because this is the path given to us. We would like to get the same path for this one, So by using x and y values, then we can write now this function. Okay, how can we do this? So remember that u was, for this case, x squared minus y squared. Okay, this is equal to x squared minus, now instead of y, we are writing x minus 1. X minus 1 squared. When you open everything up, you see that it's just 2x minus 1. Okay? So you get u. What about v? V for our case was just 2xy, 2 times xy. But now 2 times x times y, everything is written in terms of x, as you see, because now y is replaced by x minus 1. And then we get 2x squared minus 2x there. Okay? So now if we solve this equation, okay, for u and v, we can get the solution for that. So now let's write it as 2 times x, x minus 1, okay, 2x, x minus 1. Now, if you divide both sides, you get u over v, which is equal to 2x minus 1, okay, divided by 2x, x minus 1, okay. Now, when we get, when we look at this system, you see that v equals. Now let's try to solve this for u and v. Okay, u and v. In other words, 2x minus 1, 2x minus 1 will be equal to u, and 2x times x minus 1 will be equal to v. So from here, you see that now for x, for each x, you can use u inside here, and then v will be, this will be on the left hand side, u, and then some v terms. When you add them up, you can see that v equals u squared over 2 minus 1 over 2. Okay, so now v equals u squared over 2 minus 1 over 2 will be the equation for the complex plane. As you see, v is the real part, and u is the v is the imaginary part, u is the real part. So it's just the parabola, but the center is shifted. So it will be like that. Okay, so it will be just parabola. Okay, let's see. So from here to there, okay, it will be like that. Okay, it's just a parabola. This is the equation. So as you see, u equals 0, v is minus 1/2 right there, and then when u is 1, 1 over 2. Sorry, this passes from 1, 1. It passes here, okay, and then of course when u is minus 1, it's again 0. And then it goes like that. So it's like this, okay? So it's incomplete parabola, basically. So if you go in a straight line in complex plane, in the complex function plane or W plane, this corresponds to this this thing, okay? So this kind of curve. So it's square, and obviously this is going to complete to imagine the whole parabola, but it's just ending here. So point A prime there and B prime there. So this is something that we will use. So we will use this property to solve some problems. Okay. So as you see, we now have solved the system. Now we have complex plane for u and v given by these equations. Okay, and this x plus iy, which is z, if z is given by that, and u plus iv is given by this system. So basically, for this one, the straight line turned out to be a parabola in this complex function plane. Okay. So now let's find also the one of the other examples will be good for this one. Okay, now let's remove this and solve another example. So find if w equals 1 over z. This is the function. So this is a function of z, as you see, is the inverse of z. Now, if z is given by z magnitude is equal to 1, this is just the equation for circle. Okay, so what is that? The z magnitude is just x plus iy times x minus iy and the square root of it, and it gives you x squared plus y squared is equal to 1. This is just a circle, okay? This is just a circle in the complex plane, so it's right there. So it's the circle. So if this is x and this is y, okay, or as you see, the radius is just 1, this is just the circle. This is 1 and this is 1. This is just a regular circle. So now we would like to see how it is seen in the W plane if it is if the inverse of Z is taken. So okay, so if W is equal to 1 over Z, it's just 1 over X plus IY. But now we don't like to have complex thing on the denominator, so that we multiply the top and the bottom by X minus IY, okay, like that, and then the top by X minus IY. Nothing changes, but the denominator gives you just X squared plus Y squared, okay, and the top gives you just X minus IY because it's multiplied by 1. So this is it. W is given by that. So we can now separate this into real and imaginary parts. So f of Z or W is given by X over X squared plus Y squared. So this is the real part minus I, okay, times Y over square root of Y over X squared plus Y squared. Okay, so this is the imaginary part. Now, what happens is that, so we have now U, okay, this is just U equals, okay, X over X squared plus Y squared, but V equals just minus Y over X squared plus Y squared, okay? Okay, U is this. So basically, now the solution of this is just, if you take U squared plus Y squared, or V squared, sorry, if you take the squares of U and V and add them up, what you get is that X squared here divided by X squared plus Y squared, okay, plus Y squared, okay, X squared, okay, Y squared, because the square of minus y is just y squared divided by the square of this, which is x squared plus y squared squared. Okay? Now, what happens is that this is, again, x squared plus y squared divided by, okay, wait a minute, let's do this, x squared plus y squared divided by x squared plus y squared, okay, one of these cancel, and then you will get just 1 over x squared plus y squared. But one x squared plus y squared, remember, was just 1, right? Because x squared, because remember that we had this, okay, so if this is 1, this is also 1. So we solved it. So we used the property of x squared plus y squared 1 inserted here, so that u squared plus v squared is also 1. U squared plus v squared is equal to 1 is the equation in terms of u and v only. So now when we draw u here and then v there, okay, so we have exactly the same kind of circle corresponding to these passing with radius 1. This is also radius 1. So this is W plane, this is Z plane. So this corresponds to that one. So if you are moving from this point to that point, okay, it means that, say this is point A and B, the points can be A prime and B prime, something like that, okay, so you can go like that around. So basically, the paths will be the same for both Z plane and the complex plane, okay? So that's it. Today, we are done, okay, with these examples, and then we continue with the complex properties of the functions later on. Now it's going to be the end of recording, so let's just end recording.